Thank you. Thanks for a very nice introduction. I don't think I deserve this. In fact, today I will try to apply the theory that I was presenting in the previous two lectures to a field which is not my home field, to algebraic geometry. So I will try to be as much as algebraic as possible in this setting. So the topic is the Zariski locality of tilting quasi-coherent sheaves, or better, locally tilting quasi-coherent sheaves. So the idea is that in analogy to studying vector bundles, or which correspond to projective modules, so they're like locally projective quasi-coherent sheaves, you can extend this, you can apply the tilting theory to extend this notion by understanding that the zero tilting module is a projective generator. So by extending zero-dimensional case to one-dimensional, two-dimensional, etc., you define new notion of quasi-coherent sheaves along the lines as the vector bundles are defined using projective or finite projective modules, so infinite dimensional vector bundles. So this is the basic idea. And of course, the basic question, if we do that, is whether the notion is local, is independent of coordinates on the scheme. And each reasonable notion in algebraic geometry is local. And in fact, the proof that the vector bundles is a local notion is not trivial. This is a famous paper of Reynaud-Grousseau I will mention in a minute, answering a question of Grothendieck. So it's non-trivial. So also this thing is non-trivial, but it's, I mean, the basic tools are already at hand, both from tilting theory and from the Mittag-Leffler condition as derived by or developed by Reynaud and Grousseau. So this is the overview of my talk. So first I will extend the theory slightly to the non-Noetherian setting, because in algebraic geometry you are not necessarily restricted to Noetherian schemes. So that's one thing. And then I define in more detail what I mean by this Zariski locality and how can it be tested. Then we go to this Mittag-Leffler conditions, which were introduced by Grothendieck, but in more detail by Reynaud and Grousseau, and we see how the relative version of those conditions relate to tilting. And then finally we will answer the question of the locality of the notion that we introduce. So, okay, so now we slightly step up from the commutative Noetherian setting to general commutative rings. And so we need to do some generalization of the notion. So I will essentially generalize the notion of characteristic sequence and present a theorem analogous to the one that we had for commutative Noetherian rings. And for technical reasons, we will actually use the complements of the sets of primes than compared to what we did yesterday, but that's just to make the notation simpler. So the relevant notion here is the notion of a Thomason subset of the spectrum, which is just the union of the upper sets above finitely generated ideals of the ring. So this is the definition. And another notion which we need is a weaker notion than that of an associated prime ideal. And we know this weakly associated prime ideal, which is a bit mysterious notion because it says it's defined as the prime ideals such that the cyclic module R by P is contained not just in the module, but in some module in the class which is generated by M when we close it under submodules and direct limits. So this is a bit unclear what the class is. But of course, in the Noetherian setting, Thomason subsets are just the upper subsets of the spectrum, so that's exactly the subsets that we were considering. And one can show that weakly associated primes are just the associated primes. So it's really a generalization. This is not obvious, but the point is that if you add submodules and direct limits, if you add submodules, you don't change the associated prime ideals, and if you take direct limits, then if you have a map to the direct limit, since these modules R by P is finitely presented, they factor through the direct sum, the map to the direct limit, and therefore, again, there's no new associated prime in the direct limit in the Noetherian case. And now the notion of characteristic sequence slightly, dualized to the definition I had yesterday. So it's again an n-tuple of subsets of prime spectrum. This time they are included in the opposite way. So P0 contains P1, etc. And the associate primes of the cossyzygies are not contained in Pi, but they are disjoint with the Pi's. So in in the old notation, these were just the complements of those sets. So here we don't need the upper subset only, but we need Thomason subsets. So they are these particular sets. Okay. Oh, sorry, there should be weakly associated prime. So that's, sorry for this. So we need Thomason subsets rather than upper or lower subsets, depending, and we need this condition for weakly associated primes. Okay, and now the theorem holds as it did in the case of Noetherian rings, commutative Noetherian rings, namely these characteristic sequences of length n parameterize n tilting classes, and given such a characteristic sequence, you can express. Remember, we had several ways to express the tilting class, and I prefer here the way using Tor functor, because Tor functor behaves very well with direct limits and localizations. And the version that's here is that the tilting class corresponding to the characteristic sequence P0 to Pn minus 1 is just those modules where the Tor vanishes for all these cyclic modules, where ith Tor vanishes for the cyclic module R by capital I, where capital I is from the set yi, which was defined before. And the important thing, which we didn't consider in the case of Noetherian rings, but it also holds there, is that you can recover the when you have a tilting class, or more precisely the tilting module that induces the class, you can recover these sets of primes in, again, using the Tor functor, namely these are just those primes for which this condition holds, so that this Tor doesn't vanish. So here the tilting module is enough to test, and instead of cyclic modules, we take the decomposer injectives. So this we could have seen yesterday as a corollary, a slightly different notation of the theorem we had, but it extends to general commutative rings. And this is a result of Stovicek and Herbeck. They extended the work that we did earlier with Lydia. So what are the quasi-coherent sheaves in my interpretation, algebraic interpretation, and what is the Zariski locality? So quasi-coherent sheaves can be defined in several ways. We had the talk of Professor Brusa on Monday. He was speaking about the various approaches. So my approach is very algebraic. So I consider a scheme, and then you have this. I have the structure sheaf. So the structure sheaf of rings for indexed by the open affine subsets of the scheme, and a quasi-coherent sheaf is just for me it's a bunch of modules connected with some homomorphisms. So at each open affine set, you have a module over the ring from the structure sheaf corresponding to the open affine subset. That's the mu, where u is the subset. And then if you have a open affine embedded into another one, then there's a map from the module mu the other way around, so like restriction FUV, which satisfies this technical condition that if you tensor this map with the identity on RV, this induced map is an isomorphism. And of course you need compatibility of these maps. So if you compose two such maps, so you restrict from U to V and from V to W, this is the same as if you go directly from U to W. So this is I think this is a result of Inox and Estrada, that you can view the quasi-coherent sheaf, the category of quasi-coherent sheaves as the category, they call that quasi-coherent modules, but it's actually a bunch of modules. So at each open affine there's one module, and they are related in the way that's described here. So that's a quasi-coherent sheaf for me. And what are the properties of this way of presenting quasi-coherent sheaves? These functors that occur there, these tensor functors, are exact because the modules are flat. And moreover, they're actually very flat in the sense that they can be obtained. The flat module is just from iteration of localizations in elements, transfinite, possibly transfinite iteration. And the basic question, if you introduce a notion or study a notion for quasi-coherent sheaves, is whether it depends on the open affine covering of this scheme or not. So on a particular choice. So even for this representation, you can take all open affines and define the quasi-coherent sheaf as I did, or you can just take some of them that cover the scheme and cover also all the intersections of the open affines. And as this was proved by Enox and Estrada, and this will do. So this is the representation of quasi-coherent sheaves on a schema is not unique. It depends just on the way you select the covering. And of course, the less sets you need, the easier to deal with. But the question is whether the notions that you study depend on the way you cover or you select this open affine covering. Yeah, this is just a remark that if the spectrum is affine, you can just take one subset, namely this, and the quasi-coherent sheaves are nothing else than modules over this particular ring. So the quasi-coherent sheaf is the spectrum of that ring. Right. So now what kind of properties of quasi-coherent sheaves are we interested in? So we take this very simplistic approach. We take a property of modules and try to propagate it to quasi-coherent sheaves. So let's take a property of modules, and we will say P. We'll say that the quasi-coherent sheaf on a scheme is locally a P quasi-coherent sheaves, provided for each open affine subset, the module that's representing that's there has the property P as an RU module. So, for example, if P is the projective. Being the projective, this is just saying this locally projective quasi-coherent sheaf. And as I already said a couple of times, we don't want this notion to depend on the open affine covering. So this is the notion of Zariski locality. So if you have the notion of a quasi-coherent sheaf, and in particular our notion of locally P quasi-coherent sheaf, it is Zariski local if you take for any open affine covering, the quasi-coherent sheaf of M satisfies this property P for this choice of open affines covering that, if and only if it satisfies this for all but open affine subsets. So this is the notion of Zariski locality, which is not new. I mean, this is well known. Right, and of course, how to test that? Again, this is like an algebra geometric notion from algebraic geometry. We would like to understand it from the algebra point of view, and this has been done by Grusson, probably even earlier. So the relevant notion is that of an ascent-descent property. So we say that a property ascends along flat ring homomorphisms, which, if the following set is true, if you have a module which satisfies the property as an R module, and you extend it, you tensor it with S, then it will have the property as an S module. So that's the ascent of the property along flat ring homomorphisms. And the descent is required for faithfully flat ring monomorphisms. And this means that whenever you have the extended module satisfies the property as an S module, then so does the original module as an R module. So that's the descent. And it's known that for the sufficient condition for Zariski locality of a notion is the Ascent-descent property of the property P. So then this is known that the notion is correct, it's local. And in fact, there's actually an easier, you don't have to prove this ascent-descent, you can prove it in a particular case. This is called the affine communication lemma. It's in the Vakil, for example, textbook or book on algebraic geometry. So it's enough to test the ascent property along localizations in elements and the descent along the faithfully flat monomorphism, which embeds R into the product of localizations where in elements where the elements generate the ring. So that particular thing is enough. Okay, so that's what we want. And now let's see first see the classic example of Raynaud and Grusson. So the infinite dimensional vector bundle is just in my terminology, is just the quasi-coherent sheaf where all the modules sections, the modules in the open affine sets are projective. So in my terminology, these are locally projective quasi-coherent sheaves. And it's known that the notion of a vector bundle is Zariski local, so it's a correct notion. This was conjectured by Grothendieck. There's a famous French manuscript where he just writes that he needs that this is true, assume this is true, and then he continues. So he didn't have a proof. And I think I read a paper by Drinfeld where he said that the proof that was given later by Reynaud and Grusson was not known to Grothendieck, because that was already the time where he left mathematics, maybe, or didn't live in. Anyway, it's a non-trivial result. I will mention later on, because it's a source of inspiration even for this research. Okay, so let's look at what kind of property we are interested in. We are interested in the property of locally n-tilting and some of its variations. So locally n-tilting means that all the modules of sections are tilting, n-tilting. So they are, yeah, that's clear. The n-tilting is the property that we study, this three condition T1, T2, T3. And then we can also have variants of that. Locally left n-tilting means that the module of sections lives in the left class of a left tilting class of some tilting module for each open affine. And at t-tilting means that it lives in the intersection of the two classes. It doesn't make sense to speak about locally right tilting, because these notions generalize the notion of a vector bundle. Any zero tilting module is n-tilting, so it will be just a bigger class than vector bundles. While on the other side, we would have each quasi-coherent sheaf would be right n-tilting, because the right tilting class of the projectives is all modules. So these are the only options that make sense. So, okay, so why are these notions local? That's the question. Zariski local. And we know this is the case for n equals 0 by this theorem of Reynaud and Grusson for these two, for the notion of a projective module, which is so this corresponds to projective generator, so it's different, but these two correspond to projectives in 0, for n equals 0. Okay, so what's the technology that we use? And it's a kind of extension of the version of the technology that was introduced by Reynaud and Grusson. So it's the Mittag-Leffler conditions and some other tricks. So let's see. Okay, so let's have a flat ring homomorphism of commutative rings, and let's take a tilting module over R, which has these left and right tilting classes A and B, and let's see what happens with if you ascend. So if you just tensor with S, this will be an n-tilting S module. This we proved essentially yesterday. That this was my answer to the question of Roger. In that case, this was a localization, but the proof is the same. If you tensor with a flat module, it does the same proof. So this is easy to prove. So immediately we see that the property ascends along any flat ring epimorphism. So the difficult thing is to prove the descent. And so how do you do that? So the point is that so now you know this is a tilting module, so you take the corresponding tilting classes. The right one is B prime and the left one is A prime, and the tilting is T prime. And now you want to know how these classes relate to the original tilting classes. So the first result says that B prime is just the B restricted to S modules. S modules are may be viewed as contained in R modules. So if you just take all the modules in B which are S modules at the same time, then this is the B prime. So that's very easy to find. And in fact, if you have a module, an R module, it will be in the class, in the right tilting class of the original tilting module, if and only if the extended module is in the right tilting class of the extended tilting module. That's not difficult to see. What is much more difficult is to show that if this homomorphism is a faithfully flat ring monomorphism, then a similar equivalence holds for the left tilting classes, namely the module is in the left class if and only if the extended module is in the left tilting class of the extended tilting module. And the tools here are the Mittag-Leffler conditions. So I just briefly remind you what is that. Maybe I just. So the Mittag-Leffler, we will need the Mittag-Leffler conditions for inverse systems. So you have an inverse systems of modules. So in this situation, so you have some upper directed set of modules I, and for each I, small I and I, you have a module here, hi, and if j is bigger than I, then there's a homomorphism, which is denoted hij here, going in the opposite direction. So we have such a system, inverse system of modules, and we will say that this system is Mittag-Leffler if whenever you take an index, say k here, and then you look at the maps going into that module hk, indexed by k. So there is a map h ki, and there's small h, kr, small h, j, I, and so on. No, like this, ij, and this is ik. So there are homomorphisms, the compositions of these homomorphisms going into that module, and if these images of these homomorphisms stabilize in the sense that for this particular k, you find an index j here, such that the image of this map is the image of all the other maps. It doesn't decrease when you go up over the inverse over the indexing set. Then we say that this is a Mittag-Leffler module. So for countable system, this condition on the inverse system guarantees that the inverse limit is a exact functor. And now the notion of a stationary module, if you have you have now a direct system of finitely presented modules. So that's this MIFJA, the standard direct system of finitely presented modules. And you take a module B and you apply the contravariant home functor. This will create an inverse system. And then that's the system of HI, where HI is home MI to B, where MI is a member, is finitely presented member of B. And the notion relevant here, and also in the old paper by Reynaud-Grusson, is the notion of a stationary property of a module. So if you have a class of modules, now B, script B, we'll say that the module is B stationary if whenever you express this module as if there is an expression of the module as a direct limit of a system of finitely presented modules, such that if you take any module from this class script B and you apply this procedure, you take the direct system presentation, or direct limit presentation of this module M into an inverse system. This inverse system will be Mittag-Leffler. So that's a technical condition which is very, very useful, B stationarity. So that's the notion goes back to Reynaud-Grusson, but this is like a relative version where you have some class that they were using it for particular classes of modules. So what is the role of these stationary submodules? So let's be in the setting of the ascent-descent lemma. So there's this flat or faithfully flat ring homomorphism between two rings and R and S. And then you have a tilting module, tilting A module over R. You take this resolving subcategory of strongly finitely presented modules in A, and take a module and extend it. Yeah? C, and this is its extension. So for countably presented modules, we can test whether the module is in the limit closure of this set, which contains A, which is in the limit closure of that set. We can test whether it is in the left tilting class just by verifying the B stationarity. So the condition of belonging to the left class can be tested using the right class in this way. And that's very, very useful. One can prove that this is still, if I is faithfully flat, this ring homomorphism, and the C prime, the extended module, is in the limit closure of the extensions of these strongly finitely presented modules. Again, it's finitely presented. Then the original module was in the limit closure countably presented, and the original module was also countably presented and belonged to that limit closure. So again, this is equivalent to a stationarity of C prime, but over now the extended class B prime, and hence to C prime being in A prime, as we know from the earlier thing. So the key thing is that that's this fact that I already mentioned before. So this is proved really using the Mittag-Leffler theory, that if you have a faithfully flat homomorphism, then a module is in the left tilting class, if and only if the extended modulus is in the left tilting class of the extended tilting module. So that's this is maybe the technical most difficult part of the proof. And now let's go back to the problem. So of course we know now that we want to prove Zariski locality or even ascent-descent. You have a homomorphism of two commutative rings, which is flat or faithfully flat, and we want to show that the properties ascent or descent, the properties of being a tilting module or these two variants of the notion. So of course we know that the tilting modules correspond to or give rise to these characteristic sequences. So we should also study what happens with the characteristic sequences under flat base change. So this is the other part of the research. So if you have a characteristic sequence in spec R corresponding to a tilting module T, so this is this n tuple of subsets of the spectrum, there's some properties. Then you can just you can easily compute the characteristic sequence of the extended tilting module. Namely, we just take the primes that are above the what the primes from R generate in S. So this is the definition. So those primes which have this property. And conversely, if you have a tilting module, so this is always a characteristic sequence. In spec S, these QIs form such a sequence, and in fact, if you have an extended tilting module, it will always be the characteristic sequence corresponding to it is always of this particular form. So there's no other characteristic sequences occurring, though there can be other characteristic sequences occurring in spec S. But they don't come from extended tilting modules from mod R. So that's the result. And it follows then that if the extended module is a tilting module, n tilting module, then the module T satisfies conditions T1 and T2. So the first two conditions of definition of tilting module descend. So now the problem is the third condition. Okay, so so already at this stage we can prove that the notions of locally left end tilting and locally odd end tilting. So these are the notions that directly generalize the vector bundles for n equals 0. They are Zariski local for each n, and the proof is as follows. The first two conditions, they descend as I mentioned by the lemma before, by this analysis of the sequences, by this thing here, by the characteristic sequences. So the thing is the condition T3, and now here we need a more advanced technology. So one can reformulate in this setting the condition T3 using the derived category of the ring. Namely, the condition T3 in the presence of the conditions T1 and T2 is equivalent to the condition that the smallest localizing subcategory containing the T as a complex concentrated in 0 is the whole derived category. And then the proof goes how much time I have. Yeah, maybe I can just sketch the proof. And the proof uses the fact that this localizing subcategory is a tensor ideal in the derived category. Means that if you tensor it with a complex, it's closed under tensoring. Right. So, what you have to prove that the smallest localizing subcategory is the whole of T. Is the whole derived category. So what you do, right? So this is a tensor. As I said, it's a tensor idea. It contains T. So it also contains the as an R module this extended tilting module. This extended module. Now this extended tilting module is tilting. This is the assumption. We are So remember, we are proving that we have a faithfully flat ring homomorphism and a module T such that T tensor S is n-tilting S module, and we want to prove that this T is a tilting R module, and we already know that it satisfies condition T1 and T2. So certainly T is in log T, so therefore, because it's a tensor ideal, this tilting module is there, and therefore, and this tilting module has the property that the log of T prime is the derived category of S, so the S is in log T. Right, and now if in the particular this particular case is the case of Zariski locality, so this homomorphism is actually as follows. This S is a product of localizations in elements. Finite set of elements. Yeah, so that's the case. So if S is there, then also these summands are there. So all these R, F, J to minus 1 are in log T. And now you use the Czech complex, which looks like this. So they have R, there's the direct sum of R, F, J minus 1, J, and so on. And then there are overall pairs, localizations in pairs of, and finally there's the R where you localize, you invert all the elements. And this is an exact complex, and once you prove that this guy is there in log T, then by localization you can prove that also these guys are. These guys is there. This is there. By localizing, you get also this is there. So the truncated Czech complex is in the category. So let's call this C. And now the last thing is to show that this truncated Czech complex is quasi-isomorphic to the regular module, to the stock. So this means that R is in log T, but then this means, of course, that log T is the whole derived category. So this is the proof, and of course this relies very much on the particular form of this faithfully flat homomorphism, this Vakil lemma, that this S is a product, finite product of localizations of R in elements. So in that case, you can prove the result. So the notion of a locally the left n-tilting, locally at n-tilting, and in particular locally n-tilting quasi-coherent sheaves are Zariski local. So they're good notions, not depending on coordinates. And of course, we are interested in the ascent-descent condition, this algebraic condition, which so what happens then? So the result says that we can prove this in two cases. When the ring R, from which you map, is Noetherian for any n, and then in the general case of arbitrary faithfully flat ring homomorphism, but only for one tilting modules. So in both cases, we can prove that the property of being a locally n-tilting module is a ascent-descent property. So let me sketch just the first proof, because that's about the Noetherian rings, and it's the easier one. So the argument is, again, similar, but uses a very powerful theorem by Niemann, which characterizes the localizing subcategories of the derived category of a commutative Noetherian ring. So let me mention that theorem, because then it follows quite quickly. This is a result of unknown Niemann from 1992, I think, which says that the localizing subcategories so these are the subcategories closed under direct sums of dr when R is commutative Noetherian. Look as follows. So they are just the you take they are indexed by subsets of the spectrum of the ring, and for each subset you define the localizing subcategory of all complexes which for which Kp, the derived tensor over R, with the complex this is non-zero, zero, I forgot. Let me see. Oh no, this. Okay, so it's slightly different. Okay, so sorry. Well, those complexes for which the so-called homological support of the complex is a subset of P. And what is the homological support of a complex? These are all primes P, such that the derived tensor product of Kp, the residue field with this complex, is non-zero. Yeah, okay, that's. So this is a theorem proved by Niemann. So it tells you how the localizing subcategories look like. So using that, we can prove the same thing for the general case. Oops. In case the general case, by this I mean the ring homomorphism phi where R is commutative Noetherian. So the proof is as follows. So we know, that we want to prove that. We know that this is a tensor ideal, and it's a smallest localizing subcategory. So there's some subset P in the spectrum which is behind the scene. That is the log T. Right. One more thing. Yeah. So this we want to prove. Sorry. So we first look at what is the smallest derived category containing S. That may be the better strategy. What is log S as an R module? So these are for this there should be a subset P in the spectrum, such that this log S is the set of all complexes such that the homological support of X is inside P. Okay, so this should be log S. So what is the P that corresponding to S? So we'll see that the support. I claim that the homological support of the module S is actually all the spectrum of the ring, and that's because the ring homomorphism is faithfully flat. and therefore KP tensor S, this thing, which is because these are modules, this is just the normal tensor product in R, and this is non-zero because this is a faithful module, faithful homomorphism. So for all P, for each P in P, this is true. So the support of S is the whole spectrum. So the subset P corresponding to that is the whole spectrum, and therefore log S is the whole derived category of modules. And now again the same argument as before works. So if you want to see, so T is in okay, we know that log T contains log T tensor S, and that contains log S, and that's already the whole derived category. So this must be also the whole derived category, and that was to be proved. So this is the proof, which is just a few lines using this deeper result by Niemann. This is much more difficult. I'm not going to give you any details of this proof. It really goes to details of the characteristic sequences and that stuff. It just uses the other, in that case, one has the other equivalent formulation for the condition T3, namely in their module category. It's enough to prove that this so-called perpendicular category of T, the intersection of the home kernel and the X kernel, is 0. But that's some hard work. Okay, so that's it. So these are the papers that I was using in my presentation, or that are used in this research. This is the classic paper by Reynaud-Grusson answering the question of Grothendieck. This is the paper where the ideas from Reynaud-Grusson were relativized. There's a relative Mittag-Leffler conditions and related to tilting. These are papers where this was made even in a deeper form. There's 2 papers in Israel Journal of Mathematics, recent. And this is the paper which gives you the algebraic approach to quasi-coherent sheaves that I was using as a definition of quasi-coherent sheaf, in fact. This is the classification for Noetherian rings, which we had already yesterday. This is the extension to commutative rings, not necessarily Noetherian. And this last thing is a preprint, which is to appear in the Indiana University Journal of Mathematics, which is essentially the content of the second part of my talk today. Thank you.